Hey, and welcome to part 2 of parametric video equations. So last time we learned that we can create equations that my x and y coordinate are dependent upon some parameter, usually denoted by the letter t. And so that way that both x and y are dependent, and my independent variable is t. And so the question, you should have seen in the last ones that we did that, hey, these look like regular functions. Is there a way for us to express these in just x and y? And this is where I'm glad you asked. And so here we have a problem where they say, hey, I want you to write this parametric equation where y is equal to 1 over 2t and x is equal to the square root of t plus 1 in rectangular form. So when it says to write it in rectangular form, this means in y equals x mode, form, where you have a y, just like what you're normally seeing. And they want you to graph the equation, and here's the important part that we have to pay attention to. We need to state any restrictions that are on the domain. Okay, so let's go through this. So problem number 1 is I want to combine these. So the easiest way to do this is to solve one of these two equations for t. Usually you choose the one that looks the easiest. My personal thing is I like to choose x, because this way when I substitute in, I don't have to do a lot of work on the back side. Okay, I just substitute in and I call it done. So here's how I do this. So I'm going to solve this one for t. So x equals the square root of t plus 1. Undo squaring, undo square rooting, I square both sides. I get x squared is equal to t plus 1. And now I have x squared minus 1 is equal to t. Once I have that, then I can come over to my y equals. And I have a y equals 1 over 2. And what's t? Well, what t is now x squared minus 1. X squared minus 1. Ta-da! And that's it. That's my equation. So that step's not hard. The next part is taking the extra time to think about your domain. The way we think about our domain to start with is we first take a look, what were the restrictions on x in my original parametric equation? And what I should notice is that if t becomes negative, like negative 1, negative 2 specifically, I get a negative number in a square root I cannot have. So in my parametric equation, or in my parametric equation, I notice that x is always going to be greater than or equal to 0. And I keep that, and that carries through to over here. So that comes over here. So right now my domain is set up where x has to be greater than or equal to 0. After I study what the restrictions are in x in the parametric equation, then I have to take a look at, okay, so are all my values that were in my parametric equation still good over here in my new rectangular form? And what you have to see, well, hey, in this domain, if x equals 1, what happens when I plug in? Oh no, I get a 0 on the bottom, and I don't want that. So my new domain is not only x has to be greater than 0, comma, but x cannot equal 1. So if x equals 1, we're in bad shape. That is my new domain. So x has got to be greater than 0, and x cannot equal 1. So there's my restrictions on my domain. So now comes the easy part. I go into my calculator, I graph this, and so I go and graph it. Just typical y equals. No worries, no hassles. Okay, I'm going to make this here. This is 1. What ends up happening is you end up with an asymptote here at 1, because it's a rational function. My point here, when I put x is 0, I get a 1/2, or negative 1/2. So I include that. This comes down. There's my 1. I can't be 1. And There's that right there. Ta-da, there's my graph. And that's how I'll work my graph. There's my state. Okay? So that's about it. I'm not going to have any hassles or worries about anything else in this problem. Let's see what's next. Ooh. Sine and cosine. I thought we were rid of those, but we're not. Okay? It wants to write in rectangular form. So on ones that require us to use sine and cosine, or they look like this, I'm going to be a little sneaky. I'm not going to have us solve for theta because that gets ugly. You have inverse sines, inverse cosines. We're going to be sneaky. What does sneaky mean? Sneaky means we remember something. Sneaky. That is sine squared x plus cosine squared x is equal to, say it with me, 1. So, if now I do this, I say, well, wait a second. I can solve for sine. I can solve for cosine. So when I do this, I get y divided by 5 is equal to sine theta, because I just divide both sides on this one over here by 5. I come over here to this side, I divide both of these by 3, I get x over 3 is equal to cosine theta. Now if I take this equation up here and put it in with these down here, I can make something up. And so instead of saying sine squared x, I'm going to put y over 5 squared. Instead of saying cosine squared, I'm going to say x over 3 squared is equal to 1. And now I go ahead and I solve. Or I expand this out, I get y squared over 25 plus x squared over 9 is equal to 1. And hopefully you recognize that. It's been about a week. This is an equation for an ellipse. My center of the equation of my ellipse. Oh, there's nothing here for my center, so I'm at 0, 0 is my center. And then here, my major axis is the larger one, so that's going to be my a squared. All right, so that is equal to a squared. This is equal to b squared. My major axis is going to be the y's. Take the square root, it's 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then my minor axis is going to be, take the square root of 9 is 3. 1, 2, 3. 1, 2, 3. And I go ahead and I graph it. There we go. There. Make it look a little bit better. There we go. There's my ellipse. It's done. So we got to remember, if we see sine and cosine together, we've got to be a little bit sneaky. Solve for sine, solve for cosine, and use what we know. All right. Let's see what's next. Ooh. Now what they're asking us to do is take an equation and that they give us, this y equals x squared plus 2, and have a parameter, which they give us up here. Here's my parameter. And they want us to make a parametric equation out of it. Ooh, parametric equation. Okay. Hopefully, you can see that this here is going to be a parabola. It's going to be, if you will, when I graph this real fast, it's here at 2, and I have a parabola right here. That's what the graph is going to look like. That's what we're hoping it looks like after I change this into a parametric equation. So how do I do that? Well, much like we solved for t in the other one, we're going to take our parameter and solve for x and substitute it in the equation. So when I take my parameter, t is equal to x minus 1, solve for x, I find that t plus 1 is equal to x plug that into my original equation. So y is equal to, instead of x squared, I have t plus 1 squared plus 2. And if you want, you can expand this out. And then when I expand this out, y is equal to t squared plus a 2t plus a 1 plus a 2 is plus a 3. Great. Now I have my parametric equation. Boom, there's my x, there's my y. What do I set for my parameters, to restrict my t? If they don't give you any, you don't have to. But for the purpose of these next 3 problems that I want to do, okay, I'm going to change t each time to give me what I'm looking for. Because notice this problem also says, graph the equation indicating speed and orientation. The orientation part's the easy part. That's the arrows, where I start, where I finish, and writing the arrows. The speed, you have to look at the table. Okay? So what I'm going to do is, for my t, I'm going to choose -3, -2, -1, 0, and 1. I plug into x. Okay? I plug into x, so -3. -3 plus a 1 is -2. -2 plus a 1 is -1. -1 plus a 1 is a 0. 0 plus a 1 is a 1. And 1 plus a 1 is a 2. And if I did my math right, okay, when I plug in -3 for t, that's a positive 9 minus a 6. Okay, puts me at positive, positive 3 plus a 3 is 6. If I did my math right over here and expanding this, when I put in -2 for x on this equation, I should get the same thing. And lo and behold, when I put -2 for x up here, oh, I do get 6. So I did my math right when I expanded this and putting these two into each other. Okay. So I'm going to go ahead and fill out the rest of this table as I would do, like using my calculator, looking at all this. 3, 6. And I go ahead and I graph this. So again, this is not too terribly difficult. Okay, x coordinate here is 0, 2. All right, again, my start is at -3. 1, 2, 3, 6. 1, 2, 3, 4, 5, 6. All right, -2, 3. Oop, I did that wrong. Take 2. So I graph this one, -2. 1, 2, 3, 4, 5, 6. -1. 1, 2, 3. 1, 3, 2, 6. So here's my starting point. That was my finishing point. I do my orientation. And when they say indicate speed, how long did it take you to go from the beginning to the end? So how many t's did it take me? Okay, this was here. My t started at -3, ended at 1. That took 4, if you will, quote unquote, 4 seconds to go through there. Okay, great. So why is that such a big deal? Because what happens if I change this parameter up here? What if I change that but keep everything the same? How does that change either the orientation, the graph, or the timing or speed? So let's take a look. So now on this one it says use this parameter. So now I'm going to use this parameter right here. I go through the same steps. I solve for x, so t equals 2x. Solve for x. Divide both sides by 2. T over 2 is equal to x. Substitute in. Y is equal to t over 2 squared plus a 2. Square it, so it's t squared over 4 plus a 2. So again, here are my parameters, my parametric equation that I made from my parameter that I'd be able to put into my calculator. Again, because I kind of have an idea of what's going on, I'm going to change what my parameter is. And the reason why I chose these is because I wanted to have the same x's and y's that I had from the other side. So my x's and y's will not change. I'm still going to have -2, -1, 0, 1, 2. Still going to have 6, 3, 2, 3, 6. The difference is how I choose my parameter. In order now to get a -2 for x, I have to put a -4. -4 divided by 2 gives me my -2. I'm going to choose t to be -2. For -2, I plug that in. I now have -1. Hopefully see when t is 0, when t is 2, when t is 4, I get those x values, and in turn, I get the y values that come out from there. Pretty wicked cool. Huh. So now, when I graph, I still have, I still start over here at -2, 1, 2, 1, 2, 3, 4, 5, 6. So this here is 6. This is my start. -1, 3, 1, 2, 3. 0, 0. 0, 2, excuse me. 1, 3. 2, 6. There's my finish. I draw my graph. I draw the orientation. And I indicate the time that it took. So it took from -4 less than or equal to t less than or equal to 4. This time it took 8 steps to cover the same area as the other one took just 4. So hopefully you see that the speed is slower here. Why? Because it took more t's to cover this same area. Ooh. Whereas the other one, same graph as the other one that we just got done doing, but it only took 4 t's to go through that step. This one took 8 t's, twice as many. So that's how you can get speed from these graphs. Again, making the parametric graphs for physics problems amazingly easy, convenient, and easy to use. Okay? So let's go ahead and take a look at one more way. What happens when I change the parameter one more time? This time I change it to where my parameter is up here. Same y equals x plus 2 there. So how does this change? So again, t is equal to 2 minus x over 2. Add 2 to both sides. T plus 2 is equal to a negative x over 2. Multiply both sides by a -2. -2 times a t plus a 2 is equal to x. Solve both sides, multiply by -2, you got -2t. Oops, that wasn't supposed to be a plus 2. It's supposed to be a minus 2. Minus 2. -2 times a -2 is a plus a 4 is equal to x. Caught my own mistake. See, it does happen. Last but not least, how does this change for y? Get a different color. Y is equal to now x squared. So I put in there the 2t, -2t plus a 4 squared plus a 2. I'm not going to worry about expanding that out. So again, here is my parametric equation. Those two together make up my parametric equation. So those are making my parametric equation. Oh, so how is this going to change what I do on my table? T goes first, x, y. All right. Well, this time I'm going to, again, be a little bit more sneaky about what I choose for my time. I'm going to choose 1, 1.5, 2, 2.5, and 3. When I do this, my x values come out to be 2, 1, 0, -1, -2. And then I still have 6, 3, 2, 3, 6. Ooh, that's a little different. The positive and negative for the x is switched. So how does that change my parametric graph? Well, this time when I graph this, my first starting point now is at 2, 6. 1, 2, 1, 2, 3, 4, 5, 6. Here. Okay, that's my starting point now. Now I do 1, 3, 0, 2, -1, 3, -2, 6, yep. And that's my finish. So now the parameter has changed my orientation. Not only that, so again, covering the same distance that I always have, but going in the opposite direction. Okay, and then now what about my timing? My timing for this, or my speed for this, I'm going to put this over here, is now between 1 less than t less than 3. It only took 2 seconds to go from one side to the other. So it went half as fast as it went faster. So this is how, again, its speed was faster than the first one. Pretty darn cool. Okay, and this is where we're going to stop. This is the end of our day. Enjoy it. We'll see you guys in the last lecture. Bye.